Alright everyone, welcome back to a super high quality video. Let's take a look at it. So we're going to do chaotic image encryption using the logistic map. So we'll take an image, we'll use a little bit of chaos and encrypt it and be able to de-encrypt it. And if you don't know what any of that means, it's totally okay. We'll walk through it. I spent a decent amount of time on this one, just thinking about it, having fun with it. So I hope you like it. Yeah. All right, so what if we wanted to sort of securely store an image? So the goal of encryption is often to make it complicated enough that somebody couldn't just grab what you have, do something simple, and produce an output that makes your information vulnerable, right? So that's kind of where we're going to use chaos, and this chaos makes things very difficult to backtrack, just given the nature of it. And so yeah, and I also want to note that, right, like this bottom asterisk here, somebody else might have figured this out already. I didn't really check. I just had a lot of fun working through it. So I was inspired to do it from a conversation I had with a friend in grad school. So I just sat down and gave it a crack. But yeah, if there's some paper out there that already exists, then they did it first, not me. All right, so let's have a hypothetical here where, let's say you're going to go on vacation and you need somebody to come by and feed your cat, let's say a friend, and you have a fancy lock on your door, so you have a 4-digit PIN, and you want to text it to him, but he's like, no, don't do that. And when he asks you why, you're like, he's like, yeah, my dad's kind of untrustworthy. If he got the door code, he'd just go into your house, he'd take all your stuff. So he's like, try to find a way to send it to me, because I'm not going to remember it if you just tell me, but it's got to be kind of in a code, right? So my dad can't just grab it and open your door. And so you're like, all right, maybe let's try to figure out how we can do that. And so there's one of the most basic encryption techniques is just sort of this like rotation method, where you take this number line here, right? 0, 1, 2, 3, 4, 5, all the way to 9, and you just move everything over. So you move the 0 over by 2 places, you move the 1 over by 2 places, so on and so forth. And then anything that kind of falls off the edge, like the 8 and the 9 here, you just wrap it back around. And so you're like, hey, you tell your friend, what if I text you this? I text you 0531, 2, and hopefully he can work that backwards, and you show him this technique. And so how this technique works, right, is if we have this +2 and you get 0531, right, the 0 would go to a 2, the 5 would go to a 7, the 3 would go back to 5, and then 1 would go back to 3, right? So that gives us 2753, and the comma 2 tells you, okay, rotate twice, right? So that's a really basic way to sort of encrypt a number. And your friend's like, that's really good, but he's like, yeah, my dad's kind of clever. I think if you just texted him that, he'd figure it out. So he tells you to like go back to the drawing board and come up with something a little bit more complicated. And you're like, okay, how about we do this for every single digit? So instead of just doing it once, right, like the +2 that we had earlier, what if we go ahead and do it for every single number uniquely? So we'll have 0355, and we'll have 2408. So the 2408 becomes the rotation for each digit in order. Right? So +2, +4, +0, +8, that's these guys here. And then these are the numbers that you need to track backwards. So if we have the +2 and we start at 0, right, 0 goes back to 2, and that's the 2 from your first door code. And if we go from 3 on the +4, like 3 +4, that's 7, right? So that gives us that 7 back, and so on and so forth. So you could text him this string of 8 numbers. He would know, yeah, cut it in half. These become the numbers that are your code, and then these ones back here, or excuse me, this would be the key, right? So the numbers that you use, and this is the code to de-encrypt, right? Or kind of go backwards. And so he's like, all right, that works. This will be enough to like fool my dad. He won't be able to figure this out. Also, your friend's dad sounds like a horrible person, right? So in this example, right, the plus number, right, the number we're rotating those digits, and the 4-digit code, that's called a cipher, right? So this is the thing that we're using like the technique we're using. Going from the 2753 over to this, sort of larger, bigger number here. That's called encryption, and your friend reading that code, right, reading this and then doing the backward steps to get 2753 out of this, that's called decryption. And so we'll use all these basic things, plus some chaos, to go ahead and build a cipher, build a key, and then encrypt and decrypt the image. So we'll start with the logistic map. It's pretty painfully simple at first glance, right? Like, it doesn't look like there's a lot going on. You just have this sort of very basic algebra-looking equation, algebraic equation, right? And if you've never seen this notation, the n+1, the n's over here, what this is a recursive function. So you'll start with some initial pick for x, right? So an x sub 0 and x naught, right? An initial x. You'll plug that in, and then you'll process through whatever that is. You'll get some value, and now that becomes x n+1. And so then to get n plus 2, so to get the next number in this series, right, you just, our sequence, I should say, you plug this back in, so you plug in x plus 1 over here, you compute it out again, then you get x n+2, and then you put that in, you get x n+3, so on and so forth. So you're just taking whatever you got and you're plugging it back in. And so here, this value of k is, that we said, it's a parameter. Like I said, this function is recursive, and so we just loop through over and over again. And so the value of k here will do a lot of work in determining sort of what happens later on, and we'll get to that. So again, the graph of this is kind of unimpressive, right? It's just an inverted parabola if we sort of treat them as continuous. So if we put x plus 1 on this y-axis and xn on the x-axis here, we just get this arcing parabola here, right? So again, it really doesn't look like much, and it's not very exciting. But if we kind of mess with this and evaluate it, we do sort of start to see some pretty crazy behavior. And so if for one set of functions that we want to start with, we pick our x naught, our very first x, as 0.45, and we pick another x naught as 0.45001, right? These two numbers are very close to each other, so they're basically starting in the same place. So just to make this clear, right, this is where we're starting with the 0.45 or the 0.45001, right? And if we plug those in and compute out various iterations of this, right, so the number of iterations on the bottom, right, first, second, third, so on and so forth, at first they really hug each other, right? They're bouncing in tandem. There's not really any separation for the first couple of go of these. But once you start to get to about here, you can start to see that they diverge a little bit, and then they really diverge, and then it just becomes a jumbled mess where, like, sometimes they get close to each other again, sometimes they're, you know, super far apart. And this is the nature of chaos, is that these really small deltas in where you start lead to really crazy changes later on and lead to really unpredictable behavior. So this starts to look sort of random, right? It's a pseudo-randomness idea. So we'll kind of use this in a clever way to do our encryption. And if you take like a senior undergrad or an entry-level grad level math course on chaos, you'll spend like half the semester on this basically. So I'm not going to do it justice here. But just the basics are that if we take a value of k and then sort of step through, we end up creating this image. So the way this works is you say pick x naught as 0.5. So you start at 0.5, and then you run through this equation like 1,000 times or more and pick a static value of k, so a k value of, say, in this case, 2.5. If you do this, eventually, 100 iterations later, this number gets stuck on 0.6, right? So we don't see that crazy bouncing around behavior from earlier. So if I plug in, again, 0.5, or if I plug in 0.5, right, and pick k initially as 2.5, and then run this thing through, it'll land out on 0.6 and be very steady there, right? It won't deviate from this 0.6. If you keep doing this process, right, you see this sort of straight line, so we don't get any interesting behavior. And then there's this thing called a bifurcation here where it splits off. And so then it'll bounce infinitely between these two as we pick a larger value of k. So roughly between about k equals 3 and k equals, like, what is this, about 3.4. If you run this map through, eventually it'll settle out to just bouncing between these 2 points. Again, we see like sort of another splitting here, another splitting there. So it's like another bifurcation. This is called a period doubling bifurcation, right? Because it doubles each time we hit one of these little splits. And so at like roughly k is 3.5. If we run this again a bunch of times through, it'll just bounce between this value, this value, this value, and this value. So it'll just bounce around between those four. And so that's not super encrypted or impressive at that point, but we do see that it starts to get a little more complex. And then once we pick k value, that's roughly about 3.75 here, out to like 3.8, and we see this sort of like fuzzy region, right? These big fuzzy regions. This is where chaos happens. So there's a reason I picked k equals 3.75 here, because this is the chaotic region of the logistic map. So again, if you pick k values sort of in these fuzzy areas, you'll get really wild behavior, kind of like we see over on this guy. If you pick k values that are over here, you'll get really boring static dynamics that don't really change the value of xn plus 1 over time. So we're going to use this sort of fuzzy chaotic region, and we're going to abuse this to do some encryption. All right, so we sort of have the basic building blocks we need. It's not overcomplicate things if you've never looked at an image and seen how it's generated. It just uses pixel values. So each pixel gets a value, right? And here we have zeros and 255s. Different programs will treat these in different ways. But the 0 to 255, usually 0 is black, 255 is white. If this is a color, this would be black all the way to like a really bright red, or like RGB, right? Really bright green, or really bright blue. So if we take this image and we're just using grayscale, so we're just going from white to black, you can see these 255s are white and these zeros are black, and we get this sort of aggressively creepy smiley face over here. But that's all this image is, right? So in the background, when your computer grabs an image and shows it to you on a pixelated screen, right, because computers are discrete, this is the thing you would see from these numbers. All right, so how we're going to do this encryption is we'll take an image in, we're going to massage the values of all the pixels so that we can use them with the logistic map. We'll go ahead and encrypt each pixel of the image. So we'll have some process per pixel, and then we'll do it for all the pixels in the image. And then we'll be sure to store some critical data for encryption here. And so for me, I just use MATLAB. It'll import it as a uint8 as an integer value. And again, I'll just be sticking with grayscales just because it makes the code a lot easier to write and less complicated and computationally expensive. But either way, the RGB components, if you wanted to take this same thing I'm going to show and do it for a colored image, you just have to do it for each R, G, and B and then glue them all back together in the end. Okay, so how do we get these pixels that start off from 0 to 255 to be able to use them in the logistic map? So what all this gunk of just algebraic math is telling you is we're going to take all these values that go from 0 to 255 and we're going to shrink them down. This step is a little arbitrary and can be a little fudged, but I just chose 0.6. So you shrink it down to be between 0.6 and 0. So if you do 255 divided by 425, you get 0.6. And then I'm going to do a plus 0.3 here, which all this does is it just takes this and kind of shoves these values up into this range, right? So now our values are sort of where this blue bar is, right? And then if we kind of look over on the logistic map, right, we want the chaotic regions of this thing. We don't want to use anything that's not chaotic. So if we slide this over and we make sure we use values of k between like 3.7 and 3.8, right, which is roughly this reddish square, right, we can take our initial image and just shrink and squish all the values and move them around such that they start in this region here where we pick the right k, and now we'll always get chaotic dynamics out of every pixel value. All right, so Now that we know that we have that, we go, okay, we'll just run it through some number of times. Again, we'll pick the right k, and then so our p1 just becomes k times p0, 1 minus p0, right? And this is exactly the logistic map from earlier. So if we go all the way back and we look at this guy, right, it's the same equation, just now with p's instead of x's. All right, so we'll run this through, and we'll just keep doing this, right? Do this recursive equation a bunch of times, n number of times, and get to some final pn value. So our final encrypted value for that specific point becomes pn. So this is how we go from an unencrypted, just normal image, shrink the values down, run it through the logistic map, and spit out some final pn for that pixel. All right, so then if we let Pij just be a matrix of all the pixels in our image, so this is our image, right, the picture, we can do a couple of things for each pixel in our image. We can pick a single n and a single k. If you want to pause the video and think about why that's probably not a great idea, yeah, that's kind of an interesting thought experiment right there. You could pick a single n, but pick different values for k. If you also want to pause and think why maybe that isn't maybe the best idea, but would work in the end possibly, you could do that. And then what we're going to do, which is the most secure and robust method, is we're going to pick a different n and a different k for every single pixel. So this is kind of like, if we go all the way back to here, right, it's just sort of this on steroids, right? So we're, instead of doing this method where we pick one single pass for every single number in our code, in our door code, right, we're picking a different code for each value, right, that we want to secure, right? So we have a different method for this guy, we have a different method for the 7, 5, and 3, right? So with all that, just a really brief recap, right? We start with some pixel value at 0 to 255, shrink it down to be some p0, run it through the logistic map to get p1, to get p2, so on and so forth to get pn. So now, it seems simple, right? We just need to trace this process backwards. So we're going to start at pn and then go all the way back to p star. But there's a bit of a problem here, which is, it's really obvious when we take a look at, especially graphically. So if we go forwards via the encryption, right, we're using this logistic map, right, that we showed from earlier. Here's this parabola. If we start here and go, okay, we start at 0.2, this gives us roughly 0.6, and we rope this back through. So again, we're going to take this output and stick it in as our new input. So we put 0.6, put it in, it spits out, we get 0.8, and we stick in 0.8, right? We get this nice sort of circular looping pattern. So this is really easy to do in the forward direction, and there's no ambiguity. But if we do the backwards direction, right, if we start here, because this is effectively what we're doing, right, we're going from an n plus 1 back to an xn. If we start at this value, say, it's roughly, what, 0.7, and we look across, right, we see two different values that this could lead back to. And the algebra is really clear here, right? Again, this equation is nothing fancy at base level, right? It's just a second order polynomial. So if we let xn plus 1 just be this big X and xn be little x, mostly because it's just sort of easier to look at, and we just solve this out and solve the quadratic equation, right? We get this plus minus here, which tells us, hey, there are two solutions. And if we look at it graphically, yes, obviously there are two solutions, right? So we can't just simply go backwards because we don't know which value to go to. And again, because this is chaotic, if we go off by even 0.0001, right, eventually after enough iterations, this just becomes nonsense. So if we're starting off by going off by, 0.3, we're doomed from the start. So how do we get around this? Luckily what we can do is figure out which side the point is coming from. So if we go back to this image, we have a 0.2 here, and we can realize that this sort of center dividing line is 0.5. And if you mess with this equation, you'll realize that no matter how you toggle this, 0.5 is always the center, which just happens to be a nice property of this equation. So if we note that we start on the left, right, in this one, and that gives us this value, right? Then the next time we're starting on the right, and then we start on the right, right? And we can keep track of, did we pick the left point in the last step, or did we pick the right point in the last step? So here, when we go backwards, we need something telling us which of these two options to pick. But because we're the ones passing this forward, we know where it came from. So we can figure out, okay, it came from the left that time, so pick the left value. So what we need to also do in our encryption step, not the decryption step, the encryption step, is keep an array of values just telling us, hey, did it come from the left or the right? So in this case, right, if we started the encryption, we only did a single pass, right? We just did one go of this. We go from 0.3 over to like 0.7. Then when we're at 0.7 and we want to do the decryption, instead of going back and just randomly picking one of these, we would say, hey, we knew we came from the left, so go back to the left. So hopefully that's clear. So for every iteration we go forward, for every little n and n here, we're going to keep one of those backwards steps. So with all that, really what we have for our full cipher, and now the key, right, the key being the thing that tells you how to go backwards, we have the matrix of the image, right? So we have that. We have however many n's, right? And if we're going to do a different n per pixel, right, we need one n per every single pixel value. That's why the ij is there. We need a different k for every single pixel as well. So we get kij. And then during the calculations, right, we need a matrix of arrays of size n, right? So we'll have a left-right array for each value in n for the entire image, right? So for each pixel. So again, this is our key, and that's what we'll use to decrypt the image. So with all that, we can take this image and we can fully encrypt it and then fully decrypt it. So here we have this nice picture of this golden retriever, nice happy dog here, and then when we encrypt it, we just get this fuzzy, massive noise, right? There's really nothing to see here. Even if you kind of squint and know what this looked like in the beginning, it's really hard to even pretend like you can see any features left. But then when we go backwards and use that same technique, we get the exact image back. And I tested this to be sure, mathematically, right? I took the entire matrix minus the entire output matrix, and they do equal 0. So the sum of all that is 0. So it did perfectly encrypt and decrypt. So yeah, with all that being said, we'll take a look at it in MATLAB because it's kind of fun to do. So if I start, let's just kind of pick that example where we don't pick any different, don't pick a different k, and we don't pick a different n, right? We use the same one for both, right? And so I'll walk through this code. So let's clear everything out. We read in this dog image, right? We're going to make grayscale. And then this is that shrinking step, right, where we have the image, we divide it by 425, and then do the +3, right? So that's exactly what we saw in the slides. And now we have our lower bound for k, our upper bound for k, so we're picking a range of k's. We have a lower bound for n, and we have a higher upper bound for n, so I'll pick 5 here. And then from here, we'll build out, right, those k and n matrices. And then we'll loop through to do the forward pass. So this is the encrypted image that we're going to build. So we'll have something that's the same size as the image. We'll keep track of where it goes, and we'll loop through and go forward. And then this is the backwards, right? So we take everything in. I know I'm kind of going fast, but it's just a bunch of Gunko code. So yeah, we'll do the backwards, right? So we'll de-encrypt this. We'll get an image out of that, and then we'll use that to display all of it. And then the functions are really simple, right? So we have the going forward. This is that n plus 1, xn. And then on the backwards, right, because we have to keep track of it, that binary left-right choice, the way I set it up was, I think left was true and right was false. So here it's telling us of this, plus minus choice to make, this is which one you should choose. So with all that, let's go ahead and run it. All right, so this is what happens if we don't pick different values of k and n, right? We get an original image, we pass through a bunch, but we get this sort of like acid trip looking dog. It's a really cool image, right? But the problem is you can obviously tell this is kind of like some kind of animal or a dog. And the pixel values, they're just sort of jumbled, but they're not anything different, right? Because if we start with a single value and we make the same change to every value that's the same, then we're going to end up with a very similar image. So you can still see like the tongue here, you can clearly see the nose, the ears are super prominent. This is obviously just some sort of washed out background. So this is not very secure. So we can go back up here and we can set this to 3.8 and we'll leave 5 again just to see what it looks like. So now this is still not great, right? We see that the K is adding some more jumbly nonsense and mess and noise, but it needs a lot more work to get back to an encrypted state, right? So if we come back to this image right here, we see that if the K is the same, or even maybe just a touch different, but these starting values are similar, it takes us a while to get to a new, to get to sort of a jumbled mess, right? So maybe if we put in, say, we'll do 11 ends going forward and backward. We run this guy. Right, now this is a lot better. This is looking a lot better, right? We can still kind of see the general shape. It's not completely washed out, but it's going to be kind of hard to say like, oh yeah, this is totally a dog. So this isn't too bad, right? We picked a large number of N, we jumbled the K, so clearly that helps. But we had to pick a larger value of N to do so. So now let's see what happens if we pick something like, yeah, we'll do 3.7, 3.8. We'll start with a low pass of 5 and go up to, say, 15. Right, and now we get to this totally jumbled, nonsensical image where we can't tell anything. Right, and this is, again, because now we have a different K, a different N for every single pixel, and now it's going to be really hard to take a look at this and see what it's doing at all. So yeah, that's kind of it. I do like playing with these values. This can be fun to kind of just see the trippiness of what these dog images turn into afterwards, right? Oh, this one actually turned out pretty good. Yeah, I'll do 6 here. Just take a look at that. Yeah, like that just looks great, right? Looks like some real good art. Kind of hang out on my wall or something. But yeah, that's it. I hope you enjoyed it. I hope you liked it. It was a lot of fun to figure this out. I think the thing I got stuck on the most was, yeah, figuring out how to keep that value the same from forward and backward pass, especially on the decryption side, where you have to figure out how to pick the right value. But yeah, with all that being said, that's chaotic encryption using the logistic map. And yeah, hope you enjoyed it.